Hello, welcome to Cython versus SWIG. Fight! This talk is about what happens when you realize that not everything is in the standard library. In fact, there may be things you want that are not even in the cheese shop. If what you want is to use a C library from Python, then you're in luck, because Cython and SWIG are excellent tools for building Python extension modules by wrapping C libraries. But if they're both excellent, which one should you use? To answer this question, we will wrap the same library with Cython and SWIG, compare the process and results, and then you can decide. To start this talk, I'm going to quickly discuss the Python import statement and what it hides. Then we'll create a very simple library and wrap it for Python using first SWIG and then Cython. We will continue to add functions to this library and make those functions accessible from Python. As we do this, consider whether you like the SWIG way or the Cython way better. At the end, I'll make some gross generalizations, and then we'll settle the fight with a vote. I want to show a lot of code in this talk, and in an attempt to keep you, and especially me, from getting lost, I will always show the source files in the same order, and the name of the file will be in the title of the slide. First, I will show you the C code, then the SWIG interface file, and then a transcript of using the SWIG built extension module. Then I will show the Cython code, and finally a transcript of using the Cython built extension module. As we add features, I'll repeat the process. C code, SWIG demonstration, Cython code, Cython demonstration. Let's get started with the import statement. First, I have a question. What does import? Each of the import statements on the slide imports a module, but what exactly is being imported? Or to put it another way, after the import, what does the module object's dunder file object point to? This is a bit of a trick question, because the answer depends on the platform. But I'll give you a hint. There are three possibilities. The first possibility is the most straightforward. The import statement caused the Python interpreter to load a PYC file into memory. I'm sure you've seen PYC files before. They contain Python bytecode. The second possibility is the one we care about today. The import statement caused a Python extension module to be loaded into memory. The .so stands for shared object, and it is machine code. Nevertheless, when we import it, it looks and feels like Python code. This is a killer feature. Applications can import modules containing either Python code or compiled machine code, and the interface is exactly the same. And that's why we're here. That's what we'll be doing with SWIG and Cython. Taking compiled code that doesn't know anything about Python, wrapping it up, and turning it into Python extension modules that work just like pure Python code. There's one more possibility, and it isn't really relevant to SWIG or Cython, but I think I should mention it anyway, as it confused me the first time I went to look for a Python module on disk, and I couldn't find a corresponding .py or .pyc or .so file. So where did this module get imported from? The answer to this riddle is that some Python extension modules are linked with the Python interpreter when it is built. If a module is linked to the interpreter binary, then it won't have a dunder file attribute. To find the source for a module like this, look in the build environment of your Python interpreter. Now let's create a C library. Add is a C function which adds two integers and returns their sum. Unremarkable. But we'd like to use it from Python anyway. For C libraries, the interface to a function is declared in a header file. Here's the header file for add. As you may notice, it consists entirely of information that is also in adder.c. This kind of repetition is something to watch out for, because keeping the same information in two places makes for troublesome code maintenance. And we're going to see a lot more of that kind of repetition in the SWIG and Cython workflows. This slide shows the build process for libadder. The names in bold are the human-generated files. libadder.so is the final shared object, ready to be linked with C programs and other shared libraries. Now we will use SWIG and then Cython to create Python extension modules that wrap libadder's add function. To use SWIG, you, the programmer, have to create one file, the SWIG interface, or .i file. This is adder.i. The the SWIG interface file we created for libadder. It contains the name of the extension module that we want to build, the name of the C header file, and the contents of the C header file. Now, what do we do with this file? Let's look at a SWIG build diagram. The SWIG tool takes the C header file and the SWIG interface file, and it generates two files, the under_wrap.c file and a Python file. These files work together to convert between Python objects and C functions. We compile the SWIG-generated C file, link it to the shared object we started with, and presto, we have a Python extension module. And here's how it looks in use. We import the Python file that SWIG generated, and it imports the adder.so object. And we now have access to the C library. Magic. Now let's do the same thing, but with Cython. Like with SWIG, we start by creating an interface file. In Cython land, the interface file is a .pxd file. And it sure looks a lot like the SWIG interface file. Like the SWIG interface file, it both references the C header file and contains a copy of the C header file, except for the semicolon. So SWIG and Cython both require us to create an interface file. But in Cython, we also need to create a pyx file. I'm not going to explain the syntax of this file yet. Let's squint a little, pretend the file is Python code, and see if we can make any sense of it. Except for that C import line, which does look a lot like a regular Python import, this is Python code. The big difference is what we do with it. The next step is to feed it to Cython, to be translated to C. Let's do it. Cython takes our C header file, our interface file, and this third file we just learned about, the pyx file, and generates a single C file, cyadder.c in this case. Compile and link that, and we get an extension module that we can import at the Python prompt. Let's try it out. Import the shared module we just built, and boom, we are running C code from Python. Great. Wait, how did that happen again? Let's review. Like with SWIG, we start with a C header file and a shared object. We write a pxd file, which is Cython's interface file format. We also need to write wrapper functions in the Cython language, which we will soon see is a hybrid of C and Python. From those files, Cython generates a C file. Compile and link Cython's C file, and we have a Python extension module that we can import and use. Now let's learn how to use a C function that requires you to pass it a pointer to a struct. Here's a header file with a struct, pair, defined. Below the struct is the declaration for pair add, which takes a single argument, a pointer to a pair. Pair add returns the sum of the integers in the struct pointed to by ppair. That's pretty straightforward C code. But how can we use pair add from Python? How do we build a struct in Python? What do we tell SWIG? Here's what we add to our SWIG interface file for pair add. We just copy and paste the relevant part of the C header file. Remembering the SWIG build diagram, we use this to build the adder extension module. Let's see how we use it. Well, that's interesting. Where did that adder.pair come from? The answer is SWIG did it. If you put a struct in a SWIG interface file, SWIG creates an associated Python class. The fields in the Python object correspond to the fields in the struct. In this example, we are passing a pointer to a struct, but the same mechanism can be used with functions that return a pointer to a struct. Okay, now let's do it with Cython. Again, the Cython interface file contains the same information as the C header file. We just need to replace typedef with ctypedef and remove the braces and semicolons, and add a colon. And this is where we start to see Cython the language. Where on a line-by-line basis, or even within a line, we can switch between Python and C. Line 1 starts like a Python function. But in line 2, the cdef keyword says we are defining a variable the C way with a type and a name. In lines 3 and 4, the Python objects x and y are unwrapped into the C struct. On the last line, we call our original C function, using C's address of operator to get a pointer to the struct. And here it is in action. The Cython code you just saw can take arguments from the Python interpreter, allocate a struct, fill it in, and pass it to the pair add function, which has no idea the struct came from a Python program. Let's keep going. We need to see some of the complexity behind the magic. And a good way to dive right into a sea of complexity is to start thinking about C strings and Python. Yes, C strings, the source of all good buffer overflows. Compared to Python strings, C strings are so amazingly primitive, it's hard to even call them strings. They're fixed-sized, mutable arrays of bytes. Nevertheless, there are many C libraries that use C strings as part of their interface, and we need to understand how to handle them from Python. We'll start with a simple case. All good libraries need to report their version, so we'll make a function that returns its version as a C string. Here's the implementation. The important thing to notice is that the string itself is stored as a static variable. In this way, we can bypass the memory management of temporary C strings. We'll get to that soon enough. For SWIG, we just add this line right from the C header file to our SWIG interface file. Compile and link, and here's get version in use. Conveniently, SWIG automatically converts the C string to a Python string, a real Python string. So that seems to work pretty well. Let's try it with Cython. We start with a Cython interface file. Here in Cython land, with its modernist sensibilities, we don't need the void or the semicolon. Otherwise, it is identical to the C header file. And our addition to this Cython source file is a trivial pass-through function. The Cython version works just like the SWIG version, so that's boring. But if converting between C strings and Python strings is so easy, why do I find warnings like this in the Cython documentation? And this in the SWIG documentation? The problem is memory management. Python's is automatic. C's is manual. And that may sound academic until you start thinking about what you want to do with strings. Combine them, copy them, pass them around to your friends. And while you're having all that fun, who's keeping track of the memory you're using? To explore this, we'll add a function to libadder that takes a C string as a parameter and produces a C string as output. Here's the declaration for sGreeting, a function that creates a greeting. If you pass it Monty, it produces, "Hello, Monty." sGreeting works like sprintf. That is, sGreeting produces a greeting, but it returns the number of characters in the output string. So where does sGreeting put the greeting? In a buffer passed to it by the caller of sGreeting. This is a common pattern in C libraries. The caller allocates the memory. Here's the implementation of sGreeting. The first conditional allows callers to bypass the body of the function and just find out how big the output string will be. The pattern is the caller calls sGreeting with a null pointer, finds out how much space to allocate, allocates the space, and then calls sGreeting again, passing in a pointer to the allocated space. The second conditional checks if the buffer is big enough for the output, bailing out if it isn't. Let's use SWIG to make this function available to Python. Now, up to this point, we have seen functions that meshed perfectly with SWIG's default behavior. That is why our SWIG interface files have been just copies of the C header file. For example, by default, SWIG converts Python strings to read-only C strings. That's exactly what we want for the name parameter. But SWIG can do other things. The second line of our interface file is a macro that tells SWIG that it needs to allocate the memory and that the caller will tell it how much. Let's see what that looks like. Okay, we started with a function sGreeting that took 3 arguments and returned an integer, But here we are at the Python prompt using a function that takes 2 arguments and returns a list. SWIG did that. In the previous slide, we talked about how SWIG is able to take a size argument from the wrapped function, allocate a buffer of that size, and then pass the buffer to the C function. But you can also tell SWIG that a C parameter is an output buffer, and SWIG will remove that parameter from the function's signature and return it in a list, along with the actual return value. So in our example, the C version of sGreeting returned 12, but Hello Monty was grabbed from the outp pointer. Now let's see how to handle sGreeting's interface with Cython. Here's what we add to the Cython interface file. As with our other examples, it is almost identical to the C file, to the C header file. And here's the Cython code. Notice how long it is? We spend 3 lines doing memory allocation before we can call our C function. First, we call sGreeting with the bona fide name, but a null pointer. This lets us find out how long the greeting will be, and thus how much memory we need to allocate. In the next 2 lines, we create a Python string and convert it to a C string. After the conversion, the C string points to the buffer inside the Python string object. In this way, we can piggyback on Python's memory management. Another approach would be to call malloc and free directly. Once we have our memory, we can call our C function and get our greeting placed in C stir. Finally, the return statement implicitly converts C stir into a Python string. And here we see the benefit of writing all that code in the Cython PYX file. Our wrapped function has a perfectly Pythonic interface with no indication of all the memory management machinations that we were just mulling. Okay, we've looked at the details of how you use SWIG in Cython. Let's take a step back from the nitty-gritty and look at some of their high-level differences. SWIG will wrap C libraries for many languages besides Python. So if you are the author of a C library and you want to provide bindings for Python and Java and Ruby, SWIG is the tool. Whoops. Dry means don't repeat yourself, and both SWIG and Cython have a common weakness in that they require the programmer to maintain interface files that are near copies of C header files. In addition, as we saw, Cython requires you to create your own wrapper functions in a PYX file. That is not ideal. Nevertheless, SWIG has the best story here. If your C library has a SWIG-friendly interface, it is possible to use the C header files as the SWIG interface file. Even if you can only do this for most of your library, it can be a huge code maintenance win. Cython is great at wrapping C libraries, but its primary use is improving the performance of Python code. The ability to wrap C libraries almost comes along for free. The Cython pitch is great. Cython is Python with optional static types. The more types you add, the faster it goes. Unlike SWIG, which has its own pattern matching language for gluing together C and Python, Cython is C and Python in one file. You just need to wrap your head around the idea and change your build process. Allowing one to switch between C and Python line by line is a killer feature, as it lets one smoothly slide between C and Python as external interfaces or performance considerations dictate. After all this, if you want to run screaming away from SWIG and Cython, but you still need to use C libraries from Python, you have 2 choices. And they are both, in a sense, extreme choices compared to SWIG and Cython. You can write an extension module manually using the Python C API, just like much of the standard library. Or you can use C types, which is part of the standard library, and lets you access C libraries with a lot less ceremony, but also a lot less safety than SWIG and Cython. If you want to access a C library now, without building anything, without source code, and without even a header file, take a look at C types. Adopting a powerful tool like SWIG or Cython can be scary. At the beginning, it can be hard to see whether it will do what you want. Start small. Like with any code, work incrementally. Neither SWIG nor Cython require you to wrap an entire library. wrap one function at a time. And use distutils to build your Python extension, even if you don't use it for anything else. Distutils actually scrapes the Python makefile to ensure that it uses the right flags to compile extension modules. Someone wrote that code. Use it. And someone's been writing a lot of C libraries. Use them from Python. OK, now we'll vote. Cython versus SWIG. OK, raise your hand if you like the Cython way better. OK, and raise your hand if you like the SWIG way better. All right, that looks like a tie. OK, thanks. The code and slides are available on GitHub. I'm ready for questions.
Long way to the microphone. Just repeat my question.
Sure.
You didn't talk about actually running the SWIG machine so much. You didn't actually run an extra one.
The question is that I didn't talk about running the SWIG machine that much. OK, the SWIG tool just converts from the interface file and the header file and creates the C file and the Python file. There's no SWIG machine.
Well, but you have to run an extra process in your building process.
Yes, you have to run that extra step the question was, but you have to run an extra step, and yes, you do. There's an extra step in your build process. Oh.
Is going to turn the mic on here? Is this on? Can you guys hear me here? Okay, so first of all, I'm the creator of SWIG, just a little disclosure here. Boo, yeah. I actually think I'd never seen that C string output thing before, so I actually learned something about my own tool here. Actually, I just wanted to make a comment about kind of more of a historical perspective on the SWIG project. I would say it's very much a product of 1995, 96. At the time that I worked on that, the whole idea that you would use Python was a radical concept. I mean, I was doing supercomputing, and people were like, "You're going to use Python? We're going to cut all your funding because that's such an idiotic idea." Okay, so the whole concept of it was that you would write real code in C. C++, big manly languages like C and C++. And the whole point of the SWIG project is that you could tell those people, it's like, yeah, you just take your header file and it will turn into Python. If you don't like it, you could just throw it away. It was a very subversive kind of thing. Like, oh yeah, you write everything in C, and then the Python's this like little throwaway optional thing. So there's always this thing in the SWIG project that it was, like you could do all your work in C and this, optional Python. I'm not actually sure that's so true anymore. I mean, like for my own work, I tend to write everything in Python and then selectively go to C, and I sort of find that much more interesting model. I sort of wonder what the state of things is now, whether people are doing the latter. We're going to write everything in C and Python is throwaway. We're going to do it all in Python, and the C is just a little optional piece. So I don't know if that's a question, but it's just a comment on it. So
thank you. That's David Beasley.
Jump in here.
Thank you for saying.
So you did a great job showing these two tools, sort of in isolation, but is there any caveats to sort of using them together? Like, for example, I use Cython with numpy quite a bit, but never thought of using SWIG, but seeing the ease in which bringing in external C libraries that aren't in numpy seems a lot easier than the headache of doing all that sort of boilerplate stuff in Cython. So can you use those together, and is there any caveats in doing so?
I can't think of any caveats. There's been times when parts of the standard library use SWIG, I think. After it's built, after you've built your library, it's a Python extension module. I can't think of any caveats.
Great, thank you.
Yep.
I have to disagree with the examples you gave. Have you ever used SWIG with C++?
No, I have not.
Have you ever used SWIG where you have to do memory management that isn't exactly what SWIG expects? Have you ever had to deal with ownership in SWIG?
Those are very difficult issues. There's memory there's a lot of choices in C memory management. I chose one that's a little bit hard, but if you're dealing with something that has a long-running process where it's passing buffers back and forth, it could be
I can
think
tell you,
there's
it
cases
is a
that are not
lot
possible.
more complicated than Cython, and the other alternatives actually look better when you compare them with SWIG that way.
Okay.
And if you use C++, it is basically impossible to reuse the code like you would want to with SWIG interface files, because you can't wrap everything. So you have to selectively copy and paste definitions out of classes and structs to only wrap the bits you want.
I explicitly left C++ out because I thought that's above me.
Have you ever done any significant upgrading of SWIG versions? Because
I'm not
that
sure what
turns
you
out to be
mean.
really painful as well. So I was just, all right, that's enough, thanks.
Thank you. Thank you.
I'm kind of hurt that you didn't mention SWIG's best languages. It binds to Perl and to Tickle. But no, seriously, there's been a recent tool that has evolved called CFFI. Have you taken a look at this yet?
I've seen that it exists, but that's it. No, I have not used it.
I highly recommend taking a look. I was a skeptic until about, I think, 10:08 p.m. last night, and then at 10:09 I was a believer. So just it might be a really cool thing to check out.
It was created by Armin Rigo, who's just behind you in the line there.
Yep. All right. Thank you so much.
Thank you.
Hi. When I was doing research for trying to speed up my Python, that's kind of the feeling that I got was that if you have a C library and you want to use Python, you SWIG it. If you have Python that's slow and you want to speed it up, then you use Cython. And that's kind of what I've been using it for. My question, though, is does SWIG have the profiling tools that are built into Cython? Like there's a -a switch that gives you a web page that tells you which lines will benefit from C-ifying the line, and it's like gradiented out for you. So you get this bright yellow for loop, and it's like see the hell out of that, and you'll get a huge increase in speed. Does SWIG have tools like that that are?
I'm not aware of anything like that. I've used that too. That's a very nice tool.
Yeah, like -a, I think. It's a great tool. Okay.
It's in the Cython tutorial paper.
Yeah, answering the last question, I don't know whether there are any tools, but I wanted to make a comment on the C++. He's right about that, but it's easily solved by deleting all the C++.
Yeah.
So that's all.
You had a slide near the end there where you mentioned that using the Python C API and C types are both extreme, and you went a little bit into why you might think C types is extreme, but not using the Python C API. Can you expand on that?
Just because SWIG and Cython give you so much of a head start compared to doing it manually. That's all.
Do they both work with Python 3, and are there any differences in using them?
I looked at that just a little bit. The question is about Python 3, and they both seem to have preliminary support, but I did not use it. They both mention Python 3 and talk about it some.
Yes, I've done it. I looked at both for the Kohler.
Okay. David Beasley says SWIG is supported in Python 3.
I just want to answer the C-types question and not anything about SWIG. The problem with C-types is you write to the C ABI, so you need to know the sizes of everything. And with these solutions and with CFFI as well, you write to the API, which makes for stable code.
Excellent point. Okay, thank you very much.